Howdy, everyone, and welcome to Evening of the Stars, held by George Mason University Observatory. I can never tech right. George Mason has had this observatory since, I believe, 2010, if memory serves, and it is located on Research Hall on campus. We actually had the observatory and that silver tower built in order to accommodate our observatory. So it's on the roof of Research Hall. The white portion of the white building you see on the top is our control room. And so we can either control the telescope on site in that control room, or we can do it virtually, like we're going to be doing this evening. We can have observers in their own homes, company in their own homes, doing the observations remotely through VNC. The images that you see surrounding the Center 2 are images taken by students here at GMU using that particular telescope. We have images of the Orion Nebula, we have star clusters, we have galaxies, planetary nebula. We have all manner of objects that we have looked at using this particular telescope, and more growing, and that list is growing every day. In fact, when I look at this, it occurs to me that I really need to update this particular slide. Evening of the Stars occurs every alternating Tuesday evenings. The next Evening on the Stars will be the Tuesday after spring break, again, if memory serves. The way these are structured is we have a 30 to 45-minute talk by someone in the astronomical community related to something astronomical. And the talks are appropriate for all ages and interests. They are truly a public talk. You don't need any specific level of expertise to be able to understand them or enjoy them. Outside or after that, after a brief Q&A session, after that, we will have a 30-minute guided tour of the telescope where, if it is clear, which unfortunately it's looking like it won't be, if it's clear, we will use the telescope to directly image particular objects in the night sky. For instance, nowadays, it's a very good time of year to image the Orion Nebula in the constellation of Orion. But as I said, unfortunately, the weather really doesn't appear to be cooperating. And by the time we get around to doing the telescope tour, we fully expect it to be fully clouded over. We will, of course, check, because the weather is always uncertain, but we anticipate that this will be a closed dome tour this evening. If you're interested in what we are doing here at the observatory, I highly recommend the monthly Moon newsletter, or the Mason Observatory Outreach newsletter. It is a newsletter which highlights not only the research that we do here, but also has opportunities for attending public nights via the Northern Virginia Astronomy Club. It also talks about outreach events we do here at the observatory. And I write a section on space news, essentially something of particular interest that has happened either in terms of space exploration or discoveries of the universe sometime in the last month. So if you are interested in that sort of thing, I highly recommend you subscribing to this free newsletter. If you are interested in becoming a more influential member of our community, as it were, I encourage you to become a patron of the observatory. Dr. Plavchan and I, the director of the observatory, and I, we're fairly new to George Mason University, and one of our common goals is that we want to bring astronomy to the greater Virginia area. We want to do more in terms of outreach and in terms of allowing people to have access to the facilities that we run here. And to do that, in order to do that properly, particularly if we want to take telescopes, for example, to underserved communities, that does require a bit of money. And so if you would like to, if you're on board with those sorts of activities and you would like to help us out financially, again, I very much encourage you to become a patron of the observatory. You could do so at several different financial levels, from $50 a year for a star membership, or you can have a $5,000 lifetime membership and be a Big Bang contributor. We have a number of those here. So this is a list, a partial list of our current patrons. Personnel, again, as I said, Dr. Peter Plafjen is our director. I am Dr. Rob Parks, if I didn't already mention that. I am the deputy director here and point person in terms of our public outreach interests. We have on the call tonight, we have Kevin Collins and M. Thanyapong, both of whom are observatory graduate teaching assistants. They are really the backbone in terms of getting things actually done around the observatory. They will be in charge of actually running the telescope tour after I stop blathering on. And then we have the Friends of the Observatory student organization, which I can't recommend enough if there are students of George Mason in the audience tonight. We have Jonathan is the president, Owen is the vice president, and Kate is the secretary. And they do a fantastic job, or they've done a fantastic job of growing photo into a robust club and doing activities not only here at the observatory, but elsewhere on campus. So we are regularly having events, nighttime events, club events, where we use the 32-inch telescope to view the heavens for themselves, or use our solar telescope to actually view the sun on certain occasions. So if you are a student, again, I highly recommend looking into photo if you have any interest in astronomy. We do have a, if I may say, an impressive array of resources at our disposal. And you can find them through Discord, you can find them through the university web pages, and I believe they even have an Instagram account for those so inclined. And then who will be talking this evening? I will be rambling on. I am Dr. Rob Parks, as I've already mentioned. I obtained my PhD in astronomy from Georgia State University in 2014, where my research interest focused on young stars and magnetically active stars. Now, young stars are magnetically active, but not all magnetically active stars are young. So, in that case, both sides. Right now, I'm also beginning to assist Dr. Plavchen's research group on exoplanets, but primarily my interests are more centered on astronomy, science, communication, with an emphasis on public outreach. And with that, I would like to give the talk for this evening, which I have entitled Contributions by Women to Astronomy. Now, I would like to preface this by saying that this talk is going to be a general historical overview. I do not intend to talk about a woman's experience in astronomy. I simply wish to describe or relate the contributions that women have made to the field of astronomy. The motivation behind this is, and this data is a little old, but it is indicative of a current trend. This is data from the aughts. And if we look at the percentage of astronomy faculty who are women in departments where they offer an astronomy degree but no physics degree, so we're looking only at essentially astronomy departments. Incidentally, our department would not be counted in this. But if we look at astronomy, sole astronomy departments, what we see is even over a decade, while we see slight improvement, less than a third of professional astronomers are women at all levels of essentially academic rank, from full professor to associate to assistant to adjunct. A good less than a third are professional astronomers. And the percentage drops again according to achievement. Now, most statistics or most surveys that I've seen show growth up to around the 80s and 90s, and then it has plateaued. And I suspect, although I haven't fully verified this, I suspect that is still the case in today in the 2010s. This situation is even worse in physics. Now, I have personally seen more diversity hires. I've seen more hires of women and people of color. There's still a lack of representation or lack of diversity within our field. that I would like to ultimately see changed before I retire at some point. So to give you a clue as to the disparity or disparity of representation, if you just go to ye old Wikipedia, you can type in list of astronomers, the list of women astronomers, and you'll get this page. And it is a great page for finding out all of the women astronomers who have contributed over the years. And what kind of tickles me is that Dr. Tabby Boyajian, who was my grad student work office mate, she has made this list, and deservedly so. Tabby is a badass. She has done remarkable work in terms of stellar photometry and stellar radii, directly determining the sizes of stars using a rather complicated technique called interferometry. However, if you type in list of men astronomers, you don't get a page because that list would be ginormous. You cannot comprehensively put a list of men astronomers together on Wikipedia. That, again, it illustrates the sort of disparity between the small number of women in the field rather as opposed to the large number of men, particularly historically. So I'm going to highlight a few women. In particular, I'm going to start off with Caroline Herschel, who was born in 1750, died in 1848 at the age of 97. Now, one of the things one of the reasons why I put that there is because, incidentally, the women I have chosen to highlight all seem to be rather long-lived. Hopefully you can see this. Caroline Herschel would be described by Jane Austen as very accomplished. And in fact, early in their careers, both Caroline Herschel and her brother William traveled the German concert circuit, where Caroline was the premier singer and William Herschel was the composer of the music and also sometimes oboe player. And so that is where they got their start. It was only later in life that they actually turned to astronomical pursuits. Over her lifetime, Caroline Herschel won in 1828, she won the gold medal of the Royal Astronomical Society, the first woman to do so. In 1835, she was the first woman elected to the Royal Astronomical Society. And then in 1846, she won the Prussian gold medal for science. Now, this is a lithograph, I believe is the correct term, of William and Caroline Herschel. And really while this isn't precisely accurate, it does show the relationship between the two, in that William was the one who actually did the vast majority of the observations, and Caroline Herschel recorded those observations and then helped reduce or help analyze what those observations actually meant. This was in line or in keeping with the idea that women were too fragile to actually do the observing at the telescope. And that attitude persisted through up until about the turn of the 20th century. What did they primarily study? What did they find? They looked for comets. Comets being, at the time, comets were sort of in vogue, and it was fairly easy, or at least in terms of other fields of astronomical study, comets were fairly easy to find by people who were did not have a large expertise in the science. Here is my favorite comet of all time, which is Comet Hyakutake. And you can see the beautiful cometary tail coming off from the cometary core on the bottom right. Now, between 1786 and 1797, the pair of them found 8 comets, and they discovered 5 of them. One of those was a naked eye observation. Probably the most famous of these was Comet Nk. Now, Comet Nk was found in 1785, but it was lost. Not enough observations were initially made to confirm that it was actually in orbit. It was thought to be a comet, but we had no idea of where it would be at a later time. The Herschels were able to reacquire this comet, refine this comet, and they were able to observe it long enough that helped an orbit get established for us to realize that this was a short period comet with an orbital period of around 70 years or so. It's known as a short period comet. After this, she was given a salary of 50 pounds, annual salary of 50 pounds to assist her brother, which in 2019 money is about $8,100. So she got paid, but, not a whole lot. When she just in working with her brother, she also made other discoveries besides comets. In 1983, she discovered independently Charles Messier's 110 object. Messier was incidentally wanted to be a comet hunter, but he couldn't find any. But he did write down all the things that he initially thought were comets that didn't happen to be comets. And so Carolyn Herschel discovered the 110th object in Messier's catalog without even knowing of the Messier's catalog, because they were contemporaries. This is a galaxy, this is a dwarf galaxy, which is in orbit around the Andromeda Galaxy. In 1802, the Royal Society published a catalog, a star catalog, incidentally under her brother's name, which was the precursor to a much larger catalog called the New General Catalog. And this is a catalog of nebulae, clusters, and stars that now is tens of thousands of entries in size. This catalog that she published, or that she put together, was around 500 stars in size. So she was the impetus for a much larger, much more influential catalog to be created. After Carolyn Herschel, around 100 years later or so, we get to Harvard University in or around the beginning of the 20th century, or late 1800s, early 1900s. And here we can see a gentleman by the name of Edward Pickering. He is the director of the Harvard Observatory in, as the date would suggest, 1911, when this picture was made. He's the one that's circled, and also is the only dude there. The woman who is circled on his right, or on his left, our right, is Wilhelmina Fleming, the first woman that he hired to be what is now known, or what are now known to be Pickering's computers. Pickering received a rather substantial grant from the widow of Henry Draper, who was an amateur astronomer, was a doctor turned amateur astronomer, fairly independently wealthy. His wife gave, upon his passing, his wife gave a massive donation to Harvard in order to complete Henry Draper's cataloging of the night sky, specifically with this new technique called spectroscopy, which splits light into its component colors and can be used to do all sorts of things, chiefly of which is to determine the compositions of stars. Wilhelmina Fleming was Pickering's maid before she became the first person to be hired on by the Harvard Observatory. Now, one may ask the question, why did Pickering hire all these women? And their job, as the name would indicate, was to compute stuff. They would, very much like Carolyn Herschel, they were given observations taken by others in the field using telescopes, and then they would essentially analyze that data to look for patterns, to see if there are any physical mechanisms that might be responsible for the observations that they were seeing. And all of the women that I hired, most of the women that I hired were, except for Miss Fleming, who was his maid, most of the other women were educated. They were educated, and they had undergraduate degrees in mathematics and physics, many of them at Harvard's sister college. So why did he go this route? Why did he hire all women? But as far as I know, Pickering never wrote the reason down, but Miss Fleming had an idea. She says that sometimes I feel tempted to give up and let him try someone else, in order to have him find out what he is getting for $1,500 a year from me, compared with $2,500 from some other male assistants. Does he ever think that I have a home to keep and a family to take care of, as well as the men? But I suppose a woman has no claim to such comforts, and this is considered an enlightened age. Long story short, he can pay them half as much. So more than likely, that's why he hired only women for those postings. But there are, all of the women were exceptional. Two of them I'm going to highlight. One of them is Annie Jump Cannon. She lived to be 77 years old. She is alumna of Wesley College. In 1925, she was the first woman to get an Oxford honorary doctorate. In 1931, she was the first woman to receive the Henry Draper Medal from the work that she did due to Dr. Draper's funding. She was the first ever woman elected as an officer at the American Astronomical Society, and she was named curator of astronomical photographs at Harvard. She was the first woman to actually be paid as a staff member of Harvard University. Now, what did Ms. Cannon do? Well, one of the challenges that they had was they got all these spectra. And when you look on the screen here, you're looking at essentially 7 different spectra. And what a spectrum is again, a splitting of white light into its component colors, very much like passing light through a prism. But when we look at stars, that prismatic coverage, or that prismatic separation, has what we refer to as dark absorption lines in them. And those dark absorption lines correspond to particular elements. Spectrum are chemical fingerprints as to the compositions of these stars. And so they knew this. They knew that the stars were made up of different types of elements, but they were trying to figure out some way to catalog these stars or to understand these stars based on the spectra in some kind of physical way, some kind of way that actually made physical sense, that we would have a better or deeper understanding of what was intrinsically going on. Now, this project was worked on by another one of the computers extensively, and it was a very, very intensive catalog that this woman put together, and it was based on the strength of those hydrogen lines that you see there. And it was, like I said, it was very intensive. It was a large system. Stars with the strongest hydrogen lines were labeled A all the way down to Z. And so there was a lot of things going on. But unfortunately, strength of the hydrogen lines really wasn't a very good, we really had no intuitive feeling of what that really means, because we know that it doesn't mean, it's not related to the abundance of the hydrogen gas. It's simply a consequence of temperature. And that's what led Annie Jump Cannon to realize temperature, aha, that's the secret. And she reordered the system, and she threw out most of the categories, and she revised it so that the O-type stars are the hottest stars, followed by B, followed by A, F, G, K, and M. So now the spectral classification system that we still use to this day has the fundamental underpinnings of temperature. So if you take the spectrum of a temperature, not only now can you determine the composition, but you can also determine the intrinsic temperature and brightness of that object. Now, as mnemonics go, it is said that a Princeton alum came up with this in a sort of derisive sort of way, but the mnemonic that has been sticking around is for OBAFGKM. The spectral system in decreasing temperature is "Oh, be a fine girl, kiss me." There's a better mnemonic out there, but I've gotten to the point now that I don't need mnemonics, so I rarely ever use that. So, which leads us to the Hertz-Sprung-Russell diagram. The Hertz-Sprung-Russell diagram is what naturally comes out of Cannon's work. So there were two scientists by the name of Hertz-Sprung and Russell, Einar Hertz-Sprung and Henry Russell, if my memory serves. And they used Cannon's system in order to take it a step further and see if there were any sort of trends or subcategories of stars that can be listed. And what I'm going to do is I'm going to play you a short video, which I think very well describes how, or the details behind a HR diagram.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot, but even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
When she was talking about the red stars and the blue stars, Miss Cannon's work tied the color to the temperature, and that is what allowed astronomers to develop the HR diagram and be able to study things like stellar evolution, because of we can see the color of stars, we can then infer or possibly directly measure, depending on your technique, we can directly measure the temperature of that star, and then we can move on from there. Oops. There we go. And so here we have a diagram, or an HR diagram, roughly speaking. Basically, it's just a representation of the main sequence. But one of the next implications, one of the next tools that we can use, given Ms. Cannon's work, is we can derive a parallax. We can derive a distance. And what that means is that we know fundamentally how bright these objects are supposed to be based on the temperatures that we get from the spectrum. When we look at something in the night sky, its brightness is dependent on two factors. Its intrinsic brightness, say a flood lamp versus a candle, and its distance. So you can imagine that if you put a flood lamp and a candle right next to you, the flood lamp will be blazing. It will be far brighter than the candle. But you can imagine that if you put the flood lamp far enough back, that flood lamp and that candle will achieve the same brightness, will eventually become the same brightness. And so we can use that relationship to derive a distance indicator. And this method of looking at how bright something appears and how bright something is intrinsically is known as spectroscopic parallax, and is one of the ladders on our cosmic distance ladder. So from her work, we are now able to determine stellar composition. We're able to tell states of evolution. We can derive various parameters based on mass, luminosity, radius, and so forth. And now we can even determine the distances to stars. So the implications of her work are far and long-standing. One of her colleagues, Henrietta Leavitt, who unfortunately died young at the age of 53, was alumna of Vassar College. She was a member of the American Association for University Women, the American Astronomical and Astrophysical Society, and the American Association of the Advancement of Science. I am a member of two of those organizations. And she was named head of stellar photometry at Harvard University. I really won't get into just how tedious that work that she did was. Essentially, what she did, she looked at these glass plates where the stars were black dots, and the brightnesses of the stars were indicative of how, or the sizes of those black dots was indicative to how bright they were. she would have to go through tens of thousands of these plates, each containing hundreds or scores or hundreds of stars. And she would have to, by eye, determine their brightnesses over time. And then she would have to do it again for observations taken at a later date, and then again for observations taken at a later date. But in doing so, that allowed her to see something that no one else was able to see. And this is related to an object known as a Cepheid variable. Now, a Cepheid variable is a evolved star, so it's older than the sun. And for most of what we call a red giant, for most of the red giant's life, it's going to look pretty much like this. It's going to sit there. It's going to be at a constant brightness or a constant size. But eventually, the internal chemistry is going to be such that it will start to expand and it will start to cool off. And then it will rapidly start to shrink and get warm. And then it will expand, cool off, and do the same thing again. And it will do this for a very long period of time, millions of years potentially. And when it's in that variable phase, when it's in that pulsating phase, depending on its mass, it is known as a Cepheid variable. Although, if I were to be more honest, these are really pulsating variables. Cepheid is but one subtype of it. And what Henrietta Leavitt was able to see by looking at this, laboriously looking at all these glass plates, all these photographs, and all of those stars over time and time and time and time again, she noticed that some of these stars, the brightness varied significantly. And she was able to plot out by hand, mind you, the brightness of these stars over time. And she noticed that they were repetitive. They had definitive periods. And depending on the star in question, these periods of pulsations range from 1 day to all the way up to 50 days. The original variability of one single star was found in 1784 by John Goodricke, and he identified in Delta Cephei, but he was never able to find another star that behaved in exactly the same way. So Henrietta Leavitt was able to look at data from Delta Cephei and was able to basically compare this curve to others that looked very much like it. The periods would just change. And she was able to come up with what is now known as the period luminosity relationship, or the Leavitt law. Incidentally, as it happens, this is the first part of the paper. And you can see the following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt. The quote unquote end quote author of the paper is attributed to Edward Pickering, even though she did the work and she literally wrote the paper. She was not allowed to actually be able to put her name as the author. But this work is foundational to our understanding of distance, and also our understanding of the evolution of certain stars during certain portions of their lifetime. Because what she found, particularly in terms of distance, is she found this relationship, which is logarithmic, but really the take-home point is that there is a correlation between the intrinsic brightness of an object and its period. The longer the period, the brighter the object is. So if we go back to what I was saying with spectroscopic parallax, if you know the intrinsic brightness of something, in this case, we've determined it by a period rather than a spectrum, and we know how apparent brightness is, we can then again find distance. And we've used this type of relationship as standard candles. Cepheids are Lyras, Miras, all of these are different types of standard candles or pulsating variables. In 1950, Harlow Shapley was able to use this technique to map out the shape of the Milky Way galaxy and was able to determine the Earth's position was not at the center, as was previously thought. Edwin Hubble, a few years later, actually used the same method that Shapley employed, this method of standard candles, to determine the distance of the Andromeda Nebula was millions of light years away, contrary to what Shapley had said. Shapley believed that the universe was very small. And then Hubble went a little bit further, again, a few years later, and he developed the Hubble Wall, where our understanding of the universe, again, radically changed. We understood that the universe was not a static, steady state existence, but rather something that expanded with time. We have used this technique to find out the distances of stars and clusters out to 160 million light years or so. There are other techniques to get further, but Henrietta Leavitt's work, there can be a direct line between her work on pulsating stars, on Cepheid specifically, to our understanding that the universe is expanding. That is how influential or how fundamental her work was to astronomy. Then we move to more modern age, basically when Miss Leavitt and Miss Cannon were doing their work. Margaret Burbidge was born. She died fairly recently at 100 years old. She got her PhD in 1945 from University College. In 1972, she was the director of Royal Greenwich Observatory. 1976, the year of my birth, she was the first woman president of the American Astronomical Society. In 83, she received the National Medal of Science, and in 88, she became the first woman to win the Einstein World Award of Science. And there is a significant argument to be made that she should have actually won the Nobel Prize for her work. Why she wasn't, there are theories as to why. And the reason why she should have won the Nobel Prize, or the work that she did that ultimately did win a Nobel Prize, which she wasn't attributed to, was the B squared FH paper, which stood for Margaret Burbidge, her husband Geoffrey Burbidge, William Fowler, and Fred Hoyle. Fred Hoyle was Fowler was a theorist, and Fred Hoyle did the laboratory work, and then Burbidge and the Burbidges actually put it all together. Now, what am I talking about? What I'm talking about is the formation of heavy elements. During that time, during the early 1950s, the question became, where did all these, all right, so we have hydrogen and helium in the sun, vast majority of it is hydrogen and helium. So where did calcium come from? Where did oxygen come from? Where did uranium come from? Iron, for example. Where did all these heavier elements come from? Because they don't seem to be being produced in the sun, at least not now. And what they determined was that these elements are produced in stars, but over a very, very long time frame. Essentially, the star is run through nuclear fusion. It starts by burning hydrogen into helium. When that hydrogen is exhausted, that helium is then going to burn into carbon, which will then burn into oxygen, which will burn into silicon, which will burn into eventually iron. And during this process, a whole slew of different elements get created during this process. And so a lot of the heavier elements that we know of are born in stars. And the rest are essentially born in supernovae, the explosions of stars. As I am fond of saying, that is why we are all stardust. All of the elements that comprise, all the elements heavier than hydrogen and helium that you see around you, that you are composed of, were created in either the heart of a star or in the explosive aftermath of that star. Now, oops, can't teching again. So some years later, Fowler and Chandrasekhar received the Nobel Prize basically for this work. They were looking at how stars evolved and were able to codify the way that basically codify stellar evolution. And it was this work that was really instrumental in doing so. And a lot of people thought the Burbidges should have received recognition for that in the Nobel Prize. She also was able to use what we refer to as a Doppler shift to determine that galaxies actually rotate. Now, in brief, what a Doppler shift is that if light is moving towards you, it will appear to get bluer in color. If it's moving away from you, it'll appear to get redder in color. And so by looking at a galaxy, if it's distributed, you can look at the speeds of the stars on one side and the speed of the stars on the other side. One of them should be coming towards us or blue shifted. The other side should be going away from us or red shifted. And the speeds at which they're doing that, the amount of shift that we see either way, is related to the amount of mass located in that galaxy. The more massive a galaxy is, the faster it should be spinning. Which then leads us into Vera Rubin's work, the missing mass problem, which I'll talk about in a moment. And then finally, at the age of 79, Margaret Burbidge led a team using the Hubble Space Telescope and discovered that there was a supermassive black hole in the galaxy of M82. It's the first time that such a black hole was ever indirectly discovered. And what a supermassive black hole is just a really, really, really massive black hole. It's a black hole that weighs or has a mass that is millions of times or possibly billions of times the mass of the sun. Now in 2019, the Event Horizon Telescope was able to take a direct image of one of these supermassive black holes in the galaxy of M87. So this is the type of thing that Margaret Burbidge found, Dr. Burbidge found using the Hubble telescope indirectly. This is a direct image of one. And this one in particular is 6.5 billion times more massive than the sun. Lastly, I come to Vera Rubin, who lived to be 88 years old. She got her PhD from Georgetown in '54. She was a gold medal recipient of the Royal Astronomical Society in '96, the Gerber International Cosmology Prize in '02, and in '03, the Catherine Bruce Gold Medal of Astronomical Society of the Pacific. And more recently, she has been honored by the naming of a particular telescope. There was this very large telescope, well, still is. There is this very large telescope which will scan the entire sky in 3 days. It will take images of the entire northern sky every 3 days. Strike that. 3 times every day, or every night. Take-home point is that we are going to have a massive amount of data about the northern sky collected by this particular telescope, and the implications of which are numerous. It will have implications on stellar activity. It will have implications for exoplanet work. Really, I would be here for a very long time listing all of the projects that telescope is going to have something to say about it. It was originally titled romantically the LSST, or the Large Synoptic Survey Telescope, but someone in their right mind decided, no, we really need to rename this something more sensible, and now it is called the Vera Rubin Telescope in honor of her. Vera Rubin is actually was the person who, well, at least her work was my inspiration for coming into astronomy. I remember I was in the 7th grade and I read a story about her and about this work in particular, and I said, this is what I want to do with my life. What she noticed was that when you look at the velocities through redshifts that I was talking about before, and you do so in a more precise way, in a more sensitive way. And so you have measurements from the core of the galaxy regularly all the way out to the edge of the galaxy. You can create what is known as a rotation curve, or the velocity of the stars as a function of distance away from the center. Now, theoretically, if we're just talking about normal matter, this will be Keplerian in distribution, meaning, fancy way of saying, if it's further out, it's going to be slower moving. That's what we would have expected if the galaxy was only made up of stuff that we can see. But Dr. Rubin saw that that in fact the velocities tended to stay constant all the way over all distances. And the only or the best hypothesis for explaining this is matter that we cannot see. There is matter located in these galaxies, and this holds true for pretty much every galaxy that has ever been looked at, particularly every major galaxy that's ever been looked at. You have this matter, or you have this missing matter, which is driving the velocity at higher speeds at further distances away from the center. And this non-luminous matter is called dark matter. And this basically confirmed the first observation, the first suggestion that dark matter existed, made by Fritz Zwicky by looking at a similar phenomenon in terms of the speeds of galaxies within clusters. So it's still a velocity argument. Vera Rubin was able to supply even more evidence for dark matter, and because she was a nicer person than Zwicky, those observations or those conclusions were given more weight. The implications of dark matter: approximately only 90% of all matter that we know of is dark. Only 4% is in stars. So only 4%, essentially, only 4% of matter, not energy, but matter, is stuff that we can see. The vast majority of it is stuff that we can't see. We have no idea, well, we have little idea as to what that actually is. And there are two leading groups of what that might be. You have the unfortunately named acronyms MACHOs and WIMPs, the massive compact halo objects, and the weakly interacting particles. The massive compact halo objects can be explained by stuff that is just not inherently bright. Planets, really, really dim stars, dust, things of that nature. Things that we know of in our everyday astronomy live, but are just not bright enough for us to actually observe. Then you've got WIMPs, which can either be particles that we know of, like neutrinos, we know that there are a massive number of neutrinos in the universe. Just each individual neutrino is really, really massless. Doesn't have no mass, but it has a very, very tiny mass. But if you have millions upon billions of them, then that mass can eventually add up. Or potentially, we're talking about matter that isn't typical baryonic matter, that we don't know of yet. So it's still very much an open question. We do believe that it's more likely a weakly interacting particle rather than a macho that explains dark matter. But what type of weakly interacting particle is very much of an open question. And then lastly, I will end with a quote by Hawking. "I hope for the best. I have to. We have no other options." Hawking, 2018. And what I mean by that is I hope that astronomy and really every scientific field becomes more diverse because, again, I have to, because we have no other options. If we truly want growth within our fields, if we truly want more and more inventive, more and more innovation within our fields, they have to be more diverse. Study after study has found this to be true. All right. Well, thank you for your attention. Thank you for listening to me ramble on and on about this. And I will stop sharing my screen. Dun, dun, and I'll move this over here. I will be happy to take any questions. If you have any questions, please feel free to ask them. If not, then we can move on to the telescope tour of the evening.
All right. Thank you very much, Dr. Parks. I suppose I will go ahead and share my screen. All right. Can we see the observatory desktop now?
Yes, I can see it.
All right, great. Welcome everybody to the George Mason Observatory. Unfortunately, it looks like the weather has not gotten any better since the beginning of the event, so we are going to proceed with a closed dome tour of our telescope. But you can see it here on the cameras. Right now, we are looking at the desktop of the computer in the control room that we can control all of the observatory functions with. And there you can see in the top left, let me make it bigger. Here is our 32-inch telescope. That 32 inches is referring to the diameter of its primary mirror. And maybe a little bit later, I will move the telescope and point it at the camera so you can see that big mirror. But this telescope was installed in 2011, and it was brought up, it was installed in 2011. It was initially about a $300,000 investment that has had several $100,000 of upgrades put into it since then. And how it works is we have our dome here. We bring that up with the shutter that opens up and can spin a full 360 degrees. So we can point the telescope looking out through that open shutter to wherever we want in the sky. And for reference, the dome is about 20 feet or so across. And we control it not necessarily manually anymore, but just by computers. The computer we're looking at is actually on the left-hand side of this view here. This is our control room on the roof of Research Hall, where we would be if we were coming up to view the observatory in person. But we don't necessarily have to do that anymore, and we've transitioned to primarily remote observing throughout COVID. But we hope that sometime soon, maybe next semester or something, if all things go well, we might start having these events in person again. So I do want to go ahead and invite you all to please come back at your next opportunity to maybe come see us in person sometime. Let's see. This next software I'm pulling up, called the SkyX, we can use it to point our telescope wherever we want, well, almost anywhere we want in the sky. This little bullseye here is where the telescope is currently pointed. And it's a pretty easy interface, honestly. You can just point and click, and I will tell it to move. And if I come back to the cameras, we'll see the telescope will start pointing in our direction. It's pretty delicate procedure, so it moves relatively slowly. The telescope itself is around about 1,000 pounds, and it's mounted in that giant fork there that's another 1,000 pounds, and it's on a 2,000 pound base. So while it's pretty large and sturdy, it's also relatively delicate. So we want to make sure we don't move anything too quickly, because large machinery moving around could pretty easily break something if we do something wrong. So as the telescope comes into view, and I may need to move it down a little bit more, but you'll see the structure on the front of it. That is our secondary mirror. So our telescope is a reflecting telescope. Technically, the model is called a Ritchie-Cretan-Cassegrain reflecting telescope. And all those words basically just describe the mirrors in the telescope and the light that the path takes as it travels. So as the light comes in to the dome and passes into the telescope, it bounces off the primary mirror, which you can see the top of there at the back of the telescope. It's curved slightly, and so it focuses the light onto the secondary mirror here at the front, which is about a foot across. It then bounces back again through a hole in the primary mirror, which is shaped like a donut. So it's got a small hole a couple inches across in the middle, before being redirected by one final tertiary mirror into one of our various instruments. So on the back of the telescope, we have an eyepiece, just like a normal backyard telescope. Actually, let me just go ahead and we will go to the opposite side, and you can take a look. All right, so in a minute, as it comes into view, you'll see several instruments on the back of the telescope. And if we were in person, you would in fact be able to look through the eyepiece just like a regular home telescope. And you can actually see, much like a home telescope, it has a little finder scope actually on each side of it because it's so large. And that's basically just like a small scope with a much larger field of view and lower magnification that makes it easier to point the telescope manually if we need to do that. Now, in just a moment, the various instruments will start coming into view. We have the eyepiece, like I said. We also have our CCD camera, which is the primary camera we use for research or for student observational astronomy classes that take data, as well as astrophotography, things like Photo, the Friends of the Observatory Club does. There's the eyepiece now you can see on the left-hand side. On the right-hand side is the CCD camera, and what's currently facing the camera view as we see it right now is actually a low-resolution spectrograph. So that is for, like Dr. Parks mentioned during part of his talk, it's for taking the light and splitting it up by wavelength, basically the different colors like a prism, in order to see like different absorption lines that correspond to maybe like different chemical compositions of whatever object you're looking at. We also, you can see on the right-hand side there, there's our CCD camera. Between it and the last mirror, there's another kind of thin box there, and that is a filter wheel. So our camera actually only takes its images in black and white. So the light comes in and it hits the detector, and the detector basically counts the number of photons that hit it, and each pixel has a number, and that corresponds to somewhere on a scale between black and white. But we are able to produce colorized images with the telescope by using different astronomical filters. So the filters could correspond to various wavelengths: blue light, red light, ultraviolet, infrared, visual light, etc. And we can assign each of those filters a certain color. And then at the end, we can take multiple images and combine them on top of each other to make a color image. It's pretty similar to how like photo printers work, where they layer on like a red and a blue and a yellow on top of each other to make a normal color image. All right, go ahead and park the telescope back. Check the chat real quick for questions. Doesn't appear that we have any new ones about the telescope. So because of the poor weather, again, we're not going to be able to actually open up and look at anything tonight. However, M, the other observatory GTA, and Andrew, one of our observatory tour guides, will show you each a couple of images that we've actually taken using the observatory, a couple of various objects that they'll talk about, and show you some neat pictures. All right, Em, I'll turn it over to you first.
Oh, okay. I thought I'm going to give it to Andrew.
Oh, that's fine too.
Oh, yeah, I can go first if you want.
Yeah, okay.
Okay. Hello, everyone. My name is Andrew Siddall. I am an undergrad student currently, and I am majoring in astrophysics and minoring in biology. And I will be showing you and talking about some images we have of Jupiter first. And if we have some time, extra time, I will talk about Saturn. Okay. So I'm just going to pull up an image of Jupiter really quickly. Oh, here we go. So here's a pretty good image, well, relatively good image of Jupiter that we've taken in a while ago with the telescope. So as you all might know, Jupiter is actually the largest planet in our solar system, and it is really quite massive surface area wise, but it's actually really light due to the fact that it's mostly composed of hydrogen and helium, which are one of the lightest elements and one of the most abundant elements in the universe. But that is what is mostly composed of. But it also has a lot of phosphorus and sulfur also circulating in the upper atmosphere, which is what gives it these characteristic bands. This image right here is not resolved enough, but Jupiter does have a great red spot that's recently been shrinking over the years. And right now it's a little bit larger than the Earth, but it's slowly starting to shrink. But recently we've been able to find out that it is actually not going to disappear anytime soon. It's likely has a cyclic behavior. So I don't quite remember what probe or instrument was used, but scientists were able to figure out how much of the mass when it was going into the formation of the Great Red Spot relative to everything else on the planet. And they were able to figure out that it is about 300 miles deep, and it'll likely contract and grow over the years, over very long periods of time. But Jupiter is a gas giant, so in a way it is almost like you can consider it as a failed star. So gas giants take up most of the remaining gas and particles in a solar system after a star has formed and formed these large planets. And then the remaining gas and dust particles from that would form the rocky planets. But because of Jupiter being classed as a gas giant, it doesn't really have a true surface. It is basically just a giant atmosphere, a huge giant ball of sky, basically. But as you get deeper and deeper, the pressures and heat and temperature get immensely high to the point where all of the hydrogen that composes the planet starts to compact into a material what's known as metallic hydrogen. So it is we don't really have anything like that here on Earth because we don't have the pressures to be able to create like this phenomena, but hydrogen becomes almost like a soupy liquid state, and it's able to also conduct electricity really well. And that's actually the source of Jupiter's massive, immensely strong magnetic field that extends many times its diameter, much more than Earth does. Earth's magnetic field does relative to its own diameter. Jupiter is also really does quite a good job at deflecting comets and asteroids, which is probably that's theorized to be the reason why that we've probably held on to life on Earth for so long, is that we have this massive gas giant at the edge of our solar system acting like as a bodyguard, where its gravitational well is able to slingshot things out of our solar system relatively easily. Jupiter does have tons of moons, but the four main largest moons of Jupiter discovered by Galilei in the early 1600s are the four Galileo moons: Io, Callisto, Ganymede, and Europa. Now, out of those four, I'm not sure if we have any pictures of it, but Europa is particularly interesting because it may have life on it, or at least have the materials that are needed for the precursors to life. We know that because the Hubble Space Telescope was able to take pictures of it. Thank you. So here's a good image of the four Galilean moons. And there's actually five here. So one of them is not, but one of these are Europa.
I think one of them is the background star that happens to be in the field of view. Yeah.
Oh, okay. But Europa, the Hubble Space Telescope was able to take an image of it and really evaluate and find out that it has plumes of water coming out of its geysers. So we do know that it has a subsurface ocean, and it was not analyzed for its makeup, but likely it has it has life-building molecules in it, similar to not Europa, similar to Enceladus, which is one of Saturn's moons, but I can get into that more later if we have time to talk about it. So that is a candidate for life. And Callisto as well, believe it or not. Callisto was just recently found out to have a subsurface ocean as well. But it was long thought that it was very inactive due to, it has a lot of features on it that show that it should be inactive, like remnants of impacts and things like that, and the lack of weathering away of these features. But likely it also has a subsurface ocean too, which would also make it a candidate for life, at least microbial or very simple life, very deep down, away from the impact of Jupiter's dangerous magnetic fields, because you would not want to be life on the surface of any of these planets, or even an astronaut in the future, because you would just be bathed in copious amounts of extreme radiation from Jupiter. So the only way life could ever exist on any of these would be to be subsurface organisms. Does anybody have any questions about Jupiter or its moons? I could go on and on, but we don't have much time, so. James, where's the moon Io in that picture? I am not sure which one is Io, but one of those are Io. So one of them's a star in the background, and then the rest are the 4 large Galilean moons, large enough to be seen. Yep, no problem. So if anybody doesn't have any questions, I guess I'll go on to talk a little bit about Saturn.
I'll say, I believe that Io is the one that is closest to Jupiter.
Oh, the red
I know
one?
it has the closest orbit. So in this image, it's most likely the first one on the right. But that could just be a warped perspective if it's not in line with Jupiter, for example. But Io is the one that is the closest to Jupiter as far as the size of its orbit. Go ahead.
Oh yeah, thanks, Kevin. So I'm also going to talk a little bit about Saturn now, and then if there's some time, and then after that I'll pass it on to M. So here's probably the best image, or the most zoomed in image of Saturn we have right now that we've taken with the telescope. So Saturn is further out than Jupiter. It's on average is about 7 astronomical units as opposed to 5 like Jupiter. For those who don't know, keep in mind 1 astronomical unit is a distance from Earth to the Sun, which is 93 million miles. So multiply by that by about 7.2 or so, 7.5. That's the distance that we're talking about for Saturn. And Saturn is slightly smaller than Jupiter at about 9.5 times diameter, as opposed to almost 11 times the diameter of the Earth for Jupiter. But it's also even lighter than Jupiter. So it is an incredibly light planet. If you hypothetically had a giant bathtub full of water and you were able to put Saturn in it, it would be able to float. So, and the reason for that is because its atmospheric proportions of hydrogen and helium are even greater than Jupiter. So it is mostly made up of the lightest elements that exist. So it is incredibly light. But in absolute terms, it is still much heavier than Earth, just relatively speaking. Its density is much less. Its density and weight is much less than its size would indicate, at about 30% less dense than water. So it is incredibly light. It has a characteristic yellow hue, as you can see in this image, due to ammonia crystals in the atmosphere. And Saturn is known for its distinct rings. The only other planet that really has distinct rings are Uranus, the one planet that's basically oriented on its side. But Saturn's rings are composed mainly of water ice and other moons that likely used to exist before being broken apart by its tidal forces. And Saturn has similar activity to Jupiter when you're talking about the metallic hydrogen and how it gets much denser and soupier as you get towards the center until you get to a solid core, likely solid core. It's not 100%. We're not 100% sure what it's composed of, but likely some kind of iron or condensed small core with a huge soupy metallic hydrogen core or ocean around it, and then it would become less dense as you go outward into the atmosphere. But Saturn also has a really awesome candidate for life. It is a moon called Enceladus. So Enceladus, like Europa, is a icy moon, a lot smaller though compared to Europa. In fact, it's so small that its core is likely, based on its mass, we can extrapolate from that. The core will likely be almost like I would describe it as like a sponge or pumice-like structure, where it would be kind of porous, and it would be very easy for nutrients and minerals to be able to flow through its porous, less dense structure. And we know that because Cassini was a probe that is now decommissioned. It was dropped into Saturn, but Cassini at one point did a flyby on Europa to collect samples of its geysers. And its geysers, the water coming out of the geysers had tons of biological molecules in it, molecules that are precursors to life. The same molecules that scientists were able to use in the past to create temporary self-replicating molecules in a lab. So given the right conditions, these molecules may or may not already have turned into life already in its subsurface oceans, which is really surprising considering how small of a moon Enceladus is. So Enceladus has geysers as well in a subsurface ocean. And these subsurface oceans of these moons are basically formed by the tidal forces of these gas giants. So they have immense amount of gravity, and as they go around it, is able to kind of compress and crack them like an eggshell. Oh, sorry, I heard a voice. Did anybody have a question? Oh, I thought I heard a voice. Okay, so that is really all I have for Saturn. I did talk kind of a little bit about the moons on the side, but they're just so interesting. You know, they're candidates for life or potential ingredients for life. So they are very important as well, just as important as the planets that harbor these moons, right? But if anybody doesn't have any questions, that's all I have for Jupiter and Saturn. And then I'll just have M take it away for any objects he would like to talk about.
Okay, so that's two planets that we usually show during the closed dome tour. I think it's the two of the most spectacular planets we have in our photos. Usually during this time of the year, we cannot see these two objects. Let me see, I have this artificial night sky software to show us the perfect condition of our night sky, what we're supposed to see tonight. Okay, so I think Jupiter and Saturn right now set below our horizon already, and the only I think I can just search it. The only planet we can see during this time of the year is Uranus. I guess Neptune is also set. Yeah, Uranus will be somewhere around here, which is not very spectacular if we see it with the telescope. It will appear just as a dot, a faint dot. So I'm going to talk about the stars. Since today's talk, Dr. Parks mentioned a little bit about the Sprung-Russell diagram and some star evolution. Let me, okay. So we have here the globular cluster M92. This is recorded in monochromatic. I'm not sure which filter we use, unfortunately. But anyway, it's a globular cluster, which means it's a newborn group of stars. These are a bunch of stars that are actually close to each other, and they were formed at very similar time. So it's relatively new. The age, that age is, I think it's about 100 billion years ago, and it has a bunch of hydrogen and helium without any other heavy material, because of the young age, it doesn't have enough time to form the heavy substance at the core. Okay. When I said it's close to each other, you may be curious about what about the constellation we see in the sky. So the constellation we see here, like these three stars, they are just happen to be they happen to appear as to be close to each other on our sky, but they are not actually close. But when we talk about star cluster, like globular cluster, like this one, they actually close to each other. It's not just the way they appear on our sky. Okay, this globular cluster is about, I think it's about 27,000 light years away from us, and it has around 300,000 stars. And this is also a globular cluster called M13. Oh, about the name, M here is short for Charles Messier, the guy who made this catalog of deep sky object. Okay, so we call it deep sky because we cannot easily see. The brightness is pretty faint. Okay, this globular cluster is similar to the previous one. It's a newborn cluster. It has a bunch of hydrogen and helium atoms, and they are about the same size of stars and same number of star members in this globular cluster. It's about 22 light years away from Earth. Okay, and this one we luckily recorded in RGB filter, so it's a visible light. It's what we actually see with our naked eye if we have enough time to adjust our eye when looking through the telescope. And both star cluster are actually located in Hercules Constellation. I can show you briefly the Hercules Constellation. Okay. So I'm not sure where did it go. Oh, it goes to Pollux. So Hercules should be in the north. Maybe it's not up yet. But anyway, we should be able to see this during April. So next month, we can see those two objects. Maybe I just go ahead and type in M13. Yeah, it's not on our sky yet. It's about to rise. The software, I can get rid of this crowd. Yeah, so they are somewhere around here. Yeah, this is what it looks like in the software. Not really spectacular compared to our pre-recorded photo. The last object I have for today is Betelgeuse. This one is captured during some thin cloud block. We have it in visible filter, I guess, because we can see its actual color, the red color. So Betelgeuse is the red giant. If you remember the acronym for the spectrum, OB a fine good guy or girl, kiss me. So this one is M in the M spectrum. It has the red color, and it's the red giant, or the very, very old age. It's in its large state before it will explode. Recently, there's a discover that this Betelgeuse is going fainter and fainter. So there's a speculation that it may go explode, but then another research confirmed that it may not go explode within this 100,000 years. And Betelgeuse is called Alpha Orionis. It's in the constellation of Orion. So this is what we can actually see on today's night sky. Oops. Zoom in again. Okay. So this is the constellation Orion. This is where Betelgeuse is located. You can actually see this in the night sky in your from your own house. Okay. So when you want to find, you just try to find these three stars. We call it Orion's belt, and the four stars surrounding it is the body of Orion. This one is on the top left of the Orion's shoulder. Although it's called Alpha, it's actually fainter than Rigel. This is called Beta Orionis. I don't know why it's recorded in that way. Usually in astronomy, Alpha star is the most brightest star in the constellation. Maybe it's due to the time when it's recorded. This Betelgeuse happens to be brighter, and it's getting fainter and fainter because of its age. Okay. So I hope with these objects, you have some idea about how spectacular the night sky is, and you experience some of our captured image from the 32-inch telescope. And if you have any question, I'd be happy to answer. All right. I will hand it over to Dr. Parks.
Answer the question by James Kelly. Does the telescope have a way to program it? Its directions to conduct autonomous observations so humans don't have to be here to control it and take pictures at odd times during the night.
I can actually take this one if you want.
Sure. Yeah, please.
So yes, short answer is yes, we do. This was a project that was in the works for a long time until certain global events occurred, which vastly accelerated our timeline. So we do have a Python program that we can run that kind of automates all of the different pieces of software and inputs to them autonomously, which was first implemented in the summer of 2020. So we can now, particularly for our research observing, for our exoplanet research group, but we can basically put in a ticket with some like observing information, where the target we're going to look at is, how long we want to look at it, what exposures and what filter and things like that we want to use. And it'll just go and it will automatically use the software, the SkyX, to point the telescope, and other software we use to control the dome and the CCD camera. And it does other things like check the weather conditions, for example. And so we can set it running and then just kind of make sure that it gets on target, and then it'll just take images until we tell it to stop, or sunrise, basically, which has been much, much nicer than previous years where research students would have to go sit in the control room for hours on end to make sure that nothing goes wrong and to close everything down at the end of the night. So yeah, it was a bit of a process getting it running. It was several months of hard work before it was operational, and a few months after that before it was kind of fleshed out and relatively trustworthy. But yeah, and that was the effort largely of one or two undergraduate students that devoted a lot of time and effort into getting that running. But yeah, good question.
Okay. Well, I think that pretty much wraps it up for tonight's Evening Under the Stars. Feel free to come back during in 2 weeks or beyond, particularly when it is clear, so that we can offer you active views of the night sky, and so you can see what our telescope is actually capable of in real time. So with that being said, I wish you all a good night and peace out.